closed-loop controllers can come in many forms. Here, we will see some forms which are particularly remarkable because they have an excellent performance in many cases. Consequently, they are widely used. Remember that in a closed loop, this is the output of the system, which we measure. Here, we presume that our sensor is so good that we can even pretend that it is not there. So we take the reference that the output should follow and calculate the error, which is equal to the reference minus the output, which we presume is being measured exactly, and the controller finds the control action based upon the error. Now, the simplest law is called proportional control. In proportional control, the control action is proportional to the error. If the error is small, the control action is small. If the error is large, the control action is large. This type of control is sometimes enough, but sometimes it is also necessary to add a further term, and we will thereby get proportional integrative control. In proportional integrative control or proportional integral control, the control action is proportional to the error, but then we add another term which is proportional to the integral of the error over time. Why? Because if the error increases with time, or if it does not go to zero, the integral will keep growing and growing and growing, and consequently, thanks to this term, which is proportional to the integral, we'll, after a while, keep increasing our control action to get rid of this steady state error, which would otherwise never become zero. Another variation is called proportional derivative control or proportional differential control. And in this case, rather than adding to our proportional control a term which is proportional to the integral, we add a term which is proportional to the derivative of the error in order to time. Consequently, if the error has a sudden variation, we'll, thanks to this derivative, we will immediately detect it and try to correct it sooner. PI control is used, as I said, to eliminate steady state errors. PD control is used, as I said, to make our controller respond faster. The combination of the three is called PID control, in which the control action has three terms. One of them is proportional to the error, another one is proportional to the integral of the error over time, and another one is proportional to the derivative of the error. Applying the Laplace transform, we get this and this. We already know that the Laplace transform of a derivative is equal to this. So logically, the Laplace transform of an integral is equal to this. Our control action corresponds to this transfer function given by these three terms. This is the transfer function of a PID. How can I design a closed-loop controller? There are many techniques. Of course, we can't learn them all here, but let me give you a 5-minute overview, which I hope will be useful for you if you ever have to work in this field. There are many analytical techniques. Some of them are linear, some of them are nonlinear. Nonlinear control is usually employed with nonlinear plants, with plants that have significant nonlinearities, so important that linear controllers are not robust enough. Sometimes, rather than being preoccupied with analytical calculations, we just use some simplified tuning rules. Tuning rules are very simple rules that presuppose a very simple model for our plant and which work in, let us say, many situations. Not all of them, but for many plants, they provide us a reasonable result. Perhaps not a result as good as I might get if I should take the trouble of doing my calculations, but perhaps they will be enough. Some tuning rules are very popular with the PID controllers that I have been talking to you about in the last few minutes. Then there is optimal control. Optimal control is also a type of analytical method to design a controller in which I optimize a certain function. An obvious application for an ocean energy converter is a function that includes the power delivered to the grid. So we'll consider all the energy delivered, we will integrate this over time, and then we will subtract from here how severe our control actions have to be. Because severe control actions may wear off the equipment more often. This is just an idea, of course. If you ever study this subject in depth, you will learn more about this optimal control, which optimizes an objective function. Let me now give you the names of a few nonlinear techniques to design controllers. We have predictive control, which uses a model of the plant to try to predict what will happen in many possible situations in the future. We'll have many different options and we will use our model to try to see what happens in all these circumstances. Usually you use a variation of branch and bound to verify which of these many branches we need to explore to find the best option. We also have switching control. In switching control, I have several different controllers, and in each moment I choose one to act on my plant. So I keep switching from one to the other. This switching has to be done carefully, since switching from one controller to the other may cause stability problems. On-off control is something I have already mentioned. It is a very brutal nonlinear technique in which my control action just can just assume two values. And finally, we have latching. Latching deserves an additional explanation, even though you've probably already studied what latching is. In latching, the reference that I want to follow has a period which is much larger than the natural period which I would otherwise obtain. So what do? I let the output take its course and then latch it, or in other words, hold it still until it is time to go down fast, as always. When it gets down, then I will latch it again and hold it still again until it's time to go up with its usual speed. And in this way, I artificially and in a very brutally nonlinear way change the period of the oscillation. Of course, this oscillation, I repeat, is brutally nonlinear. Latching is a nonlinear control strategy. Notice that the corresponding velocity, if this is a position, the corresponding velocity is like this. Here it is positive, then I latch the device. Here it moves again, then I latch the device again. Here it moves, and then I latch it. This will be the pattern of velocities that I get with latching. Latching may be difficult to implement because it requires huge forces to do this. If I am trying to latch the water inside an oscillating water column, it is impossible to latch perfectly because the air inside is compressible. So in practice, my velocity will rather, because of failure to actually latch, will rather like this. With imperfect latching here. This is what happens in practice.